All right, and we're gonna look at finite integrals interpreted as area and determine bounds on the value of a definite integral. We're gonna compute the average value of a function over an interval as well, which we already started to talk about. So let's take a look at the definite integral. Essentially, this is an integral that's gonna end up just giving us a single result. We'll have indefinite ones that will get essentially an infinite number of results for, but this is the definite one. It's going to be a definite integral of f of x. That'll be our function over a to b, over that interval. And this is on the x-axis. Okay, that's the x-axis right there. And the way you essentially read this is you have this integral sum or integral sign right here. That's that right there. That is actually an elongated s for sum. And that's basically telling us to take our infinite sum. This number written down here is our lower limit of integration. This up here will be our upper limit of integration. Okay, then we have our integrand. That is I was a professor. This is your integrand. In fact, a professor of math. And if you are a teaching math major, you probably know him pretty well. Professor Denton. All right, that's your integrand. And then this over here, the little x at the end, is your variable that you're integrating with, your variable of integration. And so the way I read this, when I look at this, what I see this as is it's saying sum a bunch of rectangles. Okay, that's what this is doing. Sum a bunch of rectangles. And the rectangles, right? The rectangles are really, really thin, with a height of h of f of x. The width of that rectangle is dx. The height of that rectangle is f of x. And that's what it's telling you to do, to go through every single f of x, create a triangle of width dx, find its area, and then add them all up from A to B. All right, so what we're saying is, it's telling us to sum that we're saying, here we go, we have some sort of function. We're coming in here from A all the way out to B, and we are, I'm gonna zoom in on this for a second. We are coming in here and making little rectangles with a width of dx and a height of f of x, right? And then you go over to the next one and do dx and the new f of x, and then dx and the new f of x, just like those little rectangles we were doing last class. And so that's what it's saying to do. This f of x dx is just a really thin rectangle with a infinitesimally small width, and we're adding them all up. That's all it's saying to do. Now, how do we actually do that? That's, we'll talk about that later, but that's essentially what this notation is saying. So dx itself has a dimension, and so does f of x, and so you get an area of this, an abstract area. It's not necessarily, if you're doing something like force on the vertical axis, displacement on the horizontal axis, then you're not getting an area, you're getting the work done by it. But an area is what we're using, and we always relate it back to, and then we just extend that out to other things, okay? So this is what we have right there. So what is the meaning of this expression? Under the appropriate conditions, in the simplest situations, that's what it is right there. That taking a limit of our sum and going from there. And now what we can also set this equal to, something that'll help us, is this also, we can set this equal to the limit as n goes to infinity of our sum of k equals 1 to n. And then what f of ck is going to be f of a, that's where we're starting, plus our k term times our width. Remember doing the width b minus a over our number of intervals, or our number of little divisions, and then times delta x, which is our b minus a over n, right? That's our delta x and that's our ck. A is where we're starting with it. So that's going to be, so if we're starting at -3, we're going to go -3. K is going to start off at 1, and we're going to go to the right, essentially, from -3, one little teeny tiny amount, and take the value at that point, and then multiply it by that width. Okay, we all see that? All right, good. Every continuous function is integratable. All right. Let f of x, here we're going to go for a definition here. Let f of x be a function defined on a closed interval a, b. We say that a number j is the definite integral of f over a, b, and that j is the limit of the Riemann sums of that summation there if the following condition is satisfied. Given any number epsilon greater than 0, there is a corresponding number delta greater than 0, such that for every partition P, x0, x1, all the way through xn of AB, with our maximum P there is being less than delta, and any choice of CK in that range, we have this. So this is essentially going back to that definition of a limit, right? Remember doing that in Calculus 1, where you had to find, you were given like a epsilon and had to find a corresponding delta. That's essentially what we're saying here. We're saying if we can take that limit, right, and we subtract this off in that limit, we're gonna be bound into something. We have some measure of accuracy there. Okay, so it's kind of the limit definition of it. All right, let's take a look at an example. Okay, any questions so far? No? Okay. All right, so here we've got evaluate the definite integral, the integral of x plus 1 from -3 to 5. And so what we're going to do with this is we're going to turn this into our limit as n goes to infinity of f of ck, right? Well, yeah, that's just our f of ck, but we have x plus 1 there, right? Times delta x. Oh, oops, sorry. Let me do this. There we go. Okay, and so what's our partition here? No, I mean, like, what's our range here that we're looking at? Yeah, there we go. So let's find our partition by doing that. I said the wrong thing, I'm sorry. So if we look here, this is a what kind of graph? But I mean, what is that a graph of? Linear. Yep, just a straight line, and it has a positive slope, and it's going through +1, so it's going like that. We're starting back here at -3, and we're going all the way up here to +5, right? So something like that. And so this is where we're going. And that's what we want. And then we can go through and do this. So let's take a look. So for our partition, we're going from -3 to 5. And so my delta x has to equal the difference between those. So b minus a over our number of divisions. And in this case, this is going to be 8 over n, right? And so ck are what we're going to actually be plugging inside of our function is going to equal a plus k times b minus a over n. In this case, A is -3, right? Because this is A, this is B right up there. There, I did it in blue. So this is A, -3 plus K, and then our delta X is 8/n, right? So if you wanted, you could even write this as just K times delta X like that, if that helps you connect the two. K times delta X. It's up to you whichever way. It's the same thing. Okay, so we come down here, we want to do a sum. S equals, and we're going to do a summation from K equals 1 out to N of f of CK times delta X, which is our sum K equals 1 to N of f of -3 plus 8K/N times 8/N, right? No, I shouldn't have written that F right there. Sorry. I'll see where I erased that. The great downfall of the iPhone not having a fingerprint sensor now. Okay, everybody with me so far?
But
yeah.
Why are these boundaries K equals 1 and not K equals 0?
Why are we doing that?
Yes.
Because we're doing the right-hand limit. We're doing the right-hand side of it. If we did K equals 0, we'd be taking the left side. All right, so now, yeah, you know what I mean by that? We're taking the right side of the rectangles. Okay, so now we've got sum from K equals 1 to N of -3 plus 8K/N. That's our X, right? That's this X right here, plus 1. Okay, plus 1. And then times 8/N. (8/N). And so now we kind of just going to go through and start doing some algebra. So we've got sum K equals 1, and this becomes, this is 8K/N minus 2 times 8/N. And then we've got our sum from K equals 1 to N, and we can distribute that through, and we're going to get a 64K/N squared minus 16/N. And then we can split those sums up, right? And so this will become the sum from K equals 1 to N of 64K/N squared. I don't need that 64/N squared inside there, right? Because this is not a sum over N or 64. So I can write that 64/N squared out front. And so we have a sum over K. And then we have a sum from K equals 1 to N of just 16/N, which I guess I can just move this over. And we're basically just doing 16/N and then summing on 1 like that, right? And so last time I gave you all this result, you were supposed to try and come up with it, right? For the sum on K. I believe so. Did anybody try that? All right. Well, then I'm not going to go over it yet until y'all try it. Okay? Try it before next class. All right? It's a good exercise for you. So then this will become, and I know I gave you the actual end result. This is 64/N squared. That's that. And then our summation is N times n plus 1 over 2. And then the sum from k equals 1 to n of just over 1 is just n. So this is minus 16 over n times n, like that, which gives us a 64 n squared plus 64n over 2n squared minus 16. And then we've got to go ahead and combine these. So we need a 2n squared over here, which means this becomes 32n squared. So I have 64n squared plus 64n. Wait. N squared n 64n. Yeah, that should be right. I didn't mess that up, did I? I messed it up over here, I think. That's correct, isn't it? 64 times n squared plus 64 times n is that. That should be okay. 64n. And then minus 32n squared over 2n squared, just like that. And then this just gives us here 32n squared plus 64n over 2n squared, just like that. And now we want to take the limit. The limit as n goes to infinity of s is what? What's that going to be? Yeah, 32 over 2, right? Which we could have reduced the whole thing because that 64 is reducible, but this just becomes the 32 over 2, which is 16. All right, so that's what we say is our answer from doing this. Let's go back up here real quick. Okay, and I'll go back down there in a second, but let's look at this up here. We have two triangles essentially there, correct? This triangle goes through -1 right there. So we have this triangle here. What's the area of that triangle? What's this height up here?
36.
Did you say 36? What's 5 plus 1?
No, the height is 6.
Yes.
The,
Oh, you're telling me the area? So no, not 36. You got to do 18. 1/2 base times height, right? So it's base times height. The base is 6 from -1 to 5, and the height of that is 6. So this has an area of 18. If we come over to this other one, we have this triangle right here. It's below the x-axis, so it's going to be, we count it as a negative area. What's the area of that one? Huh? Our base is what? 2. What's our height? 4, or not?
no.
What's -3 plus 1? -2. So that's -2. We have a base of 2 and a height of 2. That's 4. We really got to go back and practice our geometry, everybody. This is Calc 2. We got to be able to find the area of a triangle. All right. 2 times 2 is 4, and then half of that is 2. And so that's essentially a -2, right? Because it's below the x-axis. So what's 18 plus -2? 16. What do we get? 16. Woo. Awesome. I was going to say that of course taking the area of the triangles is easier, but I'm not entirely sure now. All right, any questions on that? I know you have some homework questions that are kind of like this, right? So take a look at this and go through and do it. And I mean, just follow those same steps for whatever it is. Okay. All right, let's take a look over here. Interpreting limits interpreting limits of sums as integrals. So we want to express each one of these as an integral, a definite integral, rather than this summation. So if we look here, we're going from our norm of the partition, and we're summing it till it goes to 0. So this, we're taking that limit. So we would write this instead of as a limit over a summation like that. We want to turn this into a full-on integral. Our function here, you can see we have 2 ck cubed. What do you think our function is actually? CK is where we're plugging in our different values. So like if we go back to this one, we had x plus 1 and we ended up doing just CK plus 1, right? So if we come back over here, we have CK cubed. What is that going to be? X cubed. So this is 2x cubed. What am I integrating over? What's my variable of integration here? So I need to put a dx. And then what are my limits of integration? -1 to 0. There we go. Okay. Let's try this next one here together. Well, we kind of just did that one together. So you try the next one. In fact, try the next 2. There you go. Don't overthink them. They're pretty simple. Done? Yeah. Well, it should just take a moment. So what do I need to write here?
1, 0.
Which is which?
The one's on top.
Okay, so we say 0 to 1 that way. And then what?
Square 4 minus x squared.
And then what?
Dx.
And then what? What's that? Yep. Good. Got you nervous there for a second, huh? All right, what about this one? What can I write here? So the integral from -π/4 to 0, yep. Secant of x, yep. And then dx, there we go. Yeah, easy peasy. Lemon squeezy. Okay. All right. Take a look here. Rules of definite integrals. Here, hopefully these kind of just follow intuition. But the idea here is if you're integrating from A to A, your integral is going to be 0, right? You have this essentially, it's kind of weird in calculus to think about this kind of integration that we're essentially taking, you know, one of our rectangles, but saying it's 0. You know, we're adding up a bunch of zeros to get something non-zero, but it is what it is. If you're integrating from A to A, from something to itself, it's 0. Next is that constant multiple. Anytime you multiply an entire function by a constant, it just scales it all up. And so it's also going to do that to your area. It's going to scale it up. So if you have a constant multiple, zoom in on that one, you can just take it outside of the integral like that. So the integral of k times f of x dx is k times the integral of f of x dx. Here, if you're summing, if you're doing the integral of the sum of two different functions, you can actually split it into the integral of each function because they would add up like that, just like we could do with the regular summations there. And so you can see that there that it's just going to add that amount onto each one. And so it's their two areas added together. You can do them individually. Down here, if we have the integral from a to b of f of x dx plus the integral from b to c, take note, this matches that of f of x, then it's the same function as well. Then we can just do the integral from a to c. Right, so you can split it up essentially is what it's saying. So you usually the most useful way is to kind of go that way with it. If you need to split it into two different sections, you can split it into, you could split it into a negative section and a positive section. You don't need to do that, but if there was some reason, you can do that, split it up. Max min inequality. This is basically saying if you take the maximum of your function and take the area over the same range of that corresponding rectangle, and then you take the minimum and make a corresponding rectangle over that range as well, that the actual integral will be between the two areas. It'll be less than the maximum rectangle and greater than the minimum rectangle. Again, should make should make sense. And then this last one is saying if everywhere in your range one function is less than another, then that function is going to have an integral that is less than the integral of the other one, which again should make sense, right? All right. So hopefully those are kind of just common sense for you, but make sure you know them. So let's take a look here. Oh, and another common rule for working with different integrals is that right there. If you switch your limits of integration, you add a negative sign. It negates it. All right. So instead of from A to B, you go from B to A. It's the negative of it. All right. So let's take a look here. So let's use some of those rules to see if we can do this one. So given that the integral of f of x dx from -3 to 2 equals 5, and from 0 to 2 equals -1, evaluate from -3 up to 0. So we've got to figure out a way to kind of do this here. If we look at this, you can see that we can use a couple of these rules, right? In fact, we can use the rule where we combine them like this, and we can also use the rule where we can flip-flop them like that, right? So what I can do is I can take this one right here and make that 2 to 0 f of x dx equals what? 1. Okay, there we go. So now we have that. And now what we can do is we can say the integral from -3 to 0 of f of x dx is going to equal the integral from -3 to 2 of f of x dx, and then plus our integral from 2 to 0 f of x dx, just like that. You see how I switched those limits of integration? And so then this just becomes 5 plus 1, 6. Okay? So if you think about this, what we're really doing is we've got some sort of graph here, whatever this happens to be, right? Going from -3 out to 2, and that area underneath is 5. That's this part right here, right? That whole thing is 5. And then what we're doing is we're going from 0 to 2, and we're finding that's -1. So actually, I didn't even draw this properly. It should have been something more like, something like that, where it goes negative, right? And so then what we're doing is essentially subtracting that away. So anyway, we're instead of going out all the way out to 2, we're saying that negative part has to be taken off, and we're going to get that part. Okay? All right. My picture was getting ugly. I don't want to leave that there. But that's it. Make sense? So using the rules and thinking about it geometrically, and hopefully that should work. All right, let's try another one over here. Given that the integral from negative pi to pi of g of theta d theta equals pi over 4, and the integral from negative pi to pi of h of theta equals d theta equals square root of 2, evaluate the integral from negative pi to pi of negative 3 times g of theta plus pi times h of theta d theta. All right, so let's go ahead and try this one. We've got the integral from negative pi to pi of g of theta, and that's pi over 4. So if we take this right here, we rewrite this. First thing we can do is split this into two different integrals. So negative 3 times g of theta d theta, and then plus integral negative pi to pi of pi times h of theta d theta, right? That's our rule where we can split it, right? Because we have, which rule was that? That was this one right here, C. Okay, so we split them. Now we can bring any constants out in front, right? So this becomes negative 3 times our integral from negative pi to pi of g of theta d theta. And then this becomes plus pi times our integral from negative pi to pi of h of theta d theta, like that. Okay? And we know what the integral from negative pi to pi of g of theta is. It's pi over 4, right? So this becomes negative 3 times pi over 4. And then this one over here, we know what the integral from negative pi to h of theta is. It's square root of 2. So this becomes pi times the square root of 2. And so we can factor that pi out, and we have pi times negative 3/4 plus the square root of 2.
So we have to like switch bounds and forth from pi to them.
Why? Everything's negative pi to pi.
Oh, yeah.
Yeah, I don't need to mess with that at all. Okay? And you could, I guess, make it square root of 2 minus 3/4 if you were so inclined, but I don't see a benefit of that. All right. Now, let's take a look at C. Evaluate this definite integral here. I'm going to let you try this one. And I want you to do it, I believe, with rule A. Go ahead, give it a try. We got it already? I can tell a lot of you are already writing way too much. What's the answer here? 0, right? Because it's crazy complicated, but look at where we're going. We're going from 4 to 4. So C rule A, 0. Cool? So this next part, I'm going to skip. I'll come back and use this one in just a moment, but these are so simple that once we do the rules for these, like this is not anything you're ever going to want to look at again. So this is a waste of time. Okay, this whole page. Okay, those ones are really, really simple, and there is no reason to think you have to like know something. So let's take a look here at the definite integral as an area. We've already kind of used it as an area, and so let's take a look at this. So let's see what we can do here. We've got, yeah, so when it's above, it's the area above and it's positive. When it's below, it's the area below, it's negative. So let's take a look here. We're going compute and interpret each integral in terms of area. So we're going the integral of x dx from -7 to 4. What's it going to be? So we'll take a look at this. We're going from -7 all the way out to 4 right there. What's our answer going to be? Huh? Yep. Just add those two areas together. So this is -16.5. It's already there in the picture for you, right? All right, let me write that for you. Let's do this. Let's do -24.5 plus, what was it, 8? There you go. Okay. Take a look at the next one. From -7 to 0, what's it going to be? There you go. Reading it right off the picture there, huh? And from 0 to 4? 8. Good. Not so difficult there, right? Of course, if you're not given those areas, then you'll have to do your favorite thing, which was, I remember, finding the areas of triangles. Y'all seem to really like doing that. Okay. Now let's take a look at D. This is from -4 to 4. How can we do this integral? I don't want to do that. Think about what we're doing, interpreting it as an area. What is that? What is that a graph of? The top half of the circle, right? I think we all know how to find the top half of the area of a circle, right? So what we have here is a circle. What's the radius? 4. So this is -4, out to 4, up to 4. That's what we have right here, this thing, right? That's the area we want. So this integral is what? Half of the area of our circle. So it's 1/2 pi times 4 squared, 1/2 pi times 16, which is just 8 pi. So if you get a graph and you know the shape and you can do that, it's a nice shortcut. But make sure you can actually find that area. You know, it gets a little trickier when we start doing like the area underneath an x cubed or underneath a sine or a cosine or something like that. But it's not too bad. Okay. Any questions? Still doing okay so far? All right. Average value of a function. We talked about this before, where it was our sum of everything and then divided by, you know, our limits there, b minus a, of what we're, you know, what region we were looking at. So let's take a look here. Find the average value of that 4 minus x squared. So same one on, no, not the same one. The other one was 16 minus x squared. Sorry, 4 minus x squared from -2 to 2. So to get the average of f, we have to do our 1 over b minus a. In this case, that's 2 minus -2. And then our integral from -2 to 2 of our function 4 minus x squared dx, like that. This is what we need to compute. And how do I find what that integral actually is? Yeah, it's just the semicircle, right? Just like that previous one, except the radius of 2 now. So this is times 1/2 pi 2 squared. And so this is 1/8 pi times 4. So this is 4/8, which is just then pi over 2. That is the average value of that function from -2 to 2. Okay. And then part B. Find the average value of f of x equals x squared from 3 to 6. So for this one, it's that page I skipped. But essentially, and we're going to learn it more a little later, whenever you have just a function with an exponent, we're essentially asking the derivative of what gives us that, right? Not 2x. X cubed over 3, right? And so if I go to do this, if I do my average of f, this is 1/6 minus 3 integral from, what are we doing? From 3 to 6 of x squared dx. And so I'm just asking myself here, when we haven't really gotten into this yet, but I think you should have, you were doing anti-derivatives in the last time. Well, these integrals turn out to be anti-derivatives, which is why we don't need to do that page where we memorized some version of this. We can essentially just make this 1/3, and then this is x cubed over 3, like that. And then we're evaluating it from 3 to 6, like this. All right, in which case what we do is we have that 1/3, and then we're doing 6 cubed over 3 minus 3 cubed over 3, like that. That's what that evaluated from 3 to 6 is, looks like that. And if you go through and you do 6 cubed and you do 3 cubed and you take their difference and you divide them by 3, you should get 21. I'll leave that little bit of algebra for you. Okay? All right, not too bad, right? Okay, so we have about 5 or so minutes left. That's all really, I mean, I can't really start the next thing, I don't think, too much. So we'll stop right there if there aren't any questions. And then what y'all can do is